There's always this 30-second delay between the cloud and then YouTube.
I see.
Okay, fabulous. I see that it is now working. Okay. All right. So good afternoon, good morning, good evening, wherever you are in the world, and welcome to another seminar as part of the Monsoon seminar series. So today we are joined by Yogaraj Banerjee, who is going to tell us a little bit about the ITCZ today in the Indo-Australian monsoon. But before we get to that, let's just learn a little bit about Yogaraj before we get started. So Yogaraj completed their Masters of Science in Applied Geology from the University of Calcutta in Kolkata, India. And they finished their PhD in Earth Sciences from the OASIS Laboratory at the Center for Earth Sciences at the Indian Institute of Science in Bangalore, India. Their PhD research focused on carbonate clumped isotopes and traditional stable isotope analysis in terms of carbon and oxygen on estuarine mollusk shells. And then they explored paleo-environmental changes in terms of the temperature and rainfall and the seasonality as the Indian subcontinent drifted northward from the Jurassic into present day. But now Yogaraj is presently working as a postdoctoral candidate at the high-spec laboratory in the Department of Geosciences at National Taiwan University, and is currently working on reconstructing the precipitation history for the last 600,000 years over the Indo-Australian monsoon realm using rare earth elements such as neodymium and calcium ratios from foraminifera. So without further ado, let's hand it over to Yogaraj and they can tell us a little bit more about their work. So thank you.
Thank you. Thanks for your kind introduction, Tara. So let me, and good morning, good afternoon, and good evening, wherever you are. So let me start. Sorry. Can you see my screen now?
Yes, we can.
Okay. So yes, today I will be presenting, as Tara mentioned, my work on tracking the precipitation changes on the Indonesian Australian monsoon realm over the last 600 kilo year. So this is the work that I am carrying out here at the high-spec laboratory at Department of Geoscience, National Taiwan University. Sorry, this slide. Yes, sorry for the interruption. So at the NTU Geoscience Department, Taiwan, and the work that I am presenting today is actually with in collaboration with other colleagues, as for example, Dr. River Shen from National Taiwan University, Dr. Li Lo from National Taiwan University, Dr. Huizhen In from University of Louvain, Dr. Chandranath Basak from University of Delaware, and Dr. Shuing Hu from National Taiwan University. So if we are thinking about the mighty monsoon, it is actually the reversal of seasonal wind pattern. As we can see that from the figures that has been shown in the upper panel, how the wind directions are changing during the time of July and during the time of January. The red dotted lines are actually representing the position of ITCZ, that is Intertropical Convergence Zone. And as the ITCZ moves, the precipitation pattern also changes throughout the world. And that can be seen in the animation that you can see at the bottom panel of the slide. So when we are thinking about the global monsoon system, it has different components. So different subsystems are operating under, under the global monsoon system. As you can see, it has been shown in the different color or through some different color index here in this map. And our focus in today's talk is on the Indonesian Australian monsoon realm, especially the Indo-Pacific Whirlpool region. So actually, when we think about the Whirlpool region, it is a very important portion of the earth or the region of the earth, and which produces enormous amount of heat. But presently, in the context of the modern climate change, this particular region is actually experiencing different kind of change in terms of its dynamics. As for example, there are many research work that has documented documented the changes in the properties of the Whirlpool region. As for example, this paper by Crevate et al. 2009, they had shown that from 1970 to 2020, even after 2000, like over the last 5 decades, there is a continuous freshening happening at the Whirlpool region. In another study by Williams and Funk in 2011, they had shown the expansion of the Whirlpool towards the western part, and this expansion is affecting the climate of the Eastern Africa. It is leading its climatology towards more drier conditions. And also, people have documented that the storm tracks in the eastern part of the Australia is also changing. So there are several other studies are presently going on documenting the impact of the more present day climate change on the dynamics of the Whirlpool region. And as a result of these changes, it is affecting the biodiversity and the ecosystem of the Whirlpool region. These are some of the papers which had shown that starting from the coral reefs to the fish populations and the seagrass population, all of the components of the ecosystem there in the thriving or sustaining is at the Whirlpool region is getting affected by these changes. And also, these particular sectors provide is a very important or significant area in terms of global economy also. So the present changes in the climatology and also in the Whirlpool dynamics are also affecting the economy in this area. So for the sake of a safe and sustainable future, it is of great importance to understand the climatological variability that happened in this particular region through time. Now, when we talk about the climatology of this particular region, it is very much dependent or it is intrinsically related with the movement of the ITCZ, that is Intertropical Convergence Zone, that is bringing the rainfall in this region. So the past behavior of the ITCZ can help us to understand that that can provide us valuable information that will help in predicting the future. So there were many studies or number of studies have been carried out in this particular region. And in Monsoon seminar series, some of the colleagues who have done extensive research work over this region has already shared their research results and which has contributed valuable information in our knowledge bank in order to understand the evolution of the this Indo-Pacific worm pool region through time. Today, in my talk, I will be focusing, or I will be giving, I will try to give you some overview of some of the works that has been done from the high-spec and the paleoceanography group members from the NTU, like National Taiwan University's Geoscience Department over the last 10 years. I am a relatively new soldier in this team working in this particular domain. Uh, I will try my best to do the justice of the immense effort that has been given by my senior colleagues and other collaborators in depicting the past climatological variability in terms of ITCZ dynamics over the Indo-Pacific worm pool region. So in 2005, there was a cruise called Pectin, the past equatorial climate tracking the El Nino cruise that took place. And so you can see some of the pictures, and the photo quotes are to Dr. Uh, Lilo, who has kindly shared these photos with me. So you can see the MD cruise vessels and the group pics. And I will be focusing today in one of the core, which is MD052925. And the picture in the right hand panel, the rightmost panel actually, showing the core 2925 after it was getting recovered from the drilling site. So my today's talk will be focused on on some of the progress that has been made from investigating the foraminifera retrieved from the sedimentary code 292 MD052925. This is the overall regional climatology of the region. As I was mentioning, on the on the left-hand topmost panel, you can see that the overall the rainfall variability in the Indo-Pacific worm pool region from July and January ITCZ is getting marked. This is from the Zhang et al. 2020 paper. And the left-hand bottom panel, the yellow star represents the location of the core of MD052925. It is from the coastal Papua New Guinea region. In the right-hand panel, the climatological data of nearby Port Moresby has been shown. So the orange color, the orange color rectangles are actually representing the temperature variability of that particular region in the seasonal time scale, and it varies from around 28 to 26 degrees Celsius. Now, if we look at the precipitation pattern, which has been shown by the deep blue color bars, we can see that from January till April, the region receives higher rainfall as compared to the other months of the year. And the bottom panel is actually the river discharge data from the Sepik River, and it shows that the river discharge is higher during the December or January till March or April months as compared to the other months of the year. So the rainfall data and river discharge data closely mimic each other. So with an objective of understanding the ITCZ dynamics over this region, a number of studies were carried out, and I will try to give you some overviews. The first study was to understand the meridional SST dynamics of the Indo-Pacific Whirlpool region during the last termination. And this is a paper which came out in 2014 in climate dynamics. So in this particular work, what the authors first did, they carried out the empirical orthogonal function analysis on the modern SST data uh, for the sector 20 degree south to 20 degree north, and also from 100 to 180 degree east, in order to differentiate the northern part of Indo-Pacific wormhole and the southern part of Indo-Pacific wormhole. And their analysis shows that the uh, geographical equator is actually the thermal equator. So the orange dots represents the northern part of Indo-Pacific Whirlpool region, and the green points are actually representing the southern part of the Indo-Pacific Whirlpool region. And the green star in both panel A and B are representing the core location of 2925. And this is the table 2 from the main paper. And all the core location and the details have been driven here for the northern part of the Indo-Pacific Whirlpool and the southern part of the Indo-Pacific Whirlpool region that has been used in this particular study. So this is the result that the authors got. Panel A represents the 18O variability of the Ruber shells, and then panel B represents the magnesium by calcium ratios, and panel C are the delta 18 of the seawater that has been retrieved using the magnesium by calcium ratio based temperature and delta 18 of carbonate information. So what we can see that delta 18 of carbonate, it varies from -1 per mil to -2.5 per mil. For magnesium by calcium ratios, it varies from 3.5 micromole per mole to around 4.5 micromole per mole. And then for the delta 18 of seawater, it also varies from 0 per mil to 1.2 per mil. And the black colored triangles are the data points from where the C14 age datings were done. So what we can see from this figure that there are certain time periods like close to 18 kilo year, and then close to 16 kilo year, 15 kilo year, and then again close to 12 kilo year, when there was a rapid increase in the magnesium by calcium ratios. And then if we look into the delta 18 of the seawater values, then there are certain time periods in between 13 to 14 kilo year, and then again in between 11 to 12 kilo year, when the record shows that there is an abrupt decrease in terms of delta 18 of seawater values. So in this figure, the SST reconstruction from the magnesium by calcium ratios that has been done has been plotted, and those are shown by the red color points. And in the bottom panel, the blue line represents the delta 18 of seawater that has been calculated from these shells using the SST and the delta 18 of carbonate information. In the panel A, the sky blue lines are actually representing the delta D from Epicadome, and in panel B, the yellow color line are actually representing the delta 18O from NGRIP ice core. So what we can see from the upper panel, that is the panel A, that this particular from the 2925 core record, it shows that the temperature variability during the LGM is much more consistent, like it was having a similar variability, or but there was a much fluctuation happened after that, after the end of the LGM. So the end of the glacial conditions, it took place here at around 18.5 Ka, and then we can see that the onset of the glacial SST that increases in that region is also coeval with the thermal changes in the Southern Ocean. It, as it is evident from the delta D, the record that we are seeing here, and it indicates about a teleconnection between the low and high altitude realms in the Southern Hemisphere. And also what we can see that there is a significant SST increase from 1 to 2 degrees Celsius during the Henrik event 1 and the Yogaraj time period. And now if we look at the bottom panel, that is panel B, we can see that the delta 18 of seawater ice volume corrected that record, it shows that there is an increase during the Henrik event 1 and the Yogaraj time period, and it might have resulted from the weakening or the southward shift of the ITCZ during these time intervals. And also the comparison of the delta 18 of the seawater with 18 of NGRIP record shows that they goes pretty well in hand with each other, and it also indicates an imprint of high latitude Southern Hemisphere in the Solomon Sea delta 18 of the seawater record during the last termination period. In the next figure, what you can see that the orange lines are representing the stacked record of the northern part of the Indo-Pacific warm pool. The green line represents the southern part of the Indo-Pacific warm pool, and the black line is the difference between the northern and the southern part of the Indo-Pacific warm pool region. And the panel A actually represents the SST record, and panel B is the delta, like the difference in the SST between the northern and the southern part of the Indo-Pacific warm pool region. Panel C represents the delta 18 of the seawater for both this northern and the southern part of the Indo-Pacific warm pool, and panel D are actually the difference in the seawater composition between the northern stack and the southern stack. So what we can see that both the northern and the southern part of the Indo-Pacific warm pool, both the stacked record shows the same amplitude of change in terms of temperature, that is during that that is around 3 degrees Celsius between the last like from each other from during the glacial and interglacial time period. And then there is a very interesting fact that the onset of termination happened around 19 kilo year at the southern part of the Indo-Pacific warm pool, and which is around 1 kilo year earlier than the northern part of the Indo-Pacific warm pool, as at least these stack records are showing that. And this timing of the onset of the termination at the southern part is actually coeval or synchronous with the Eastern Equatorial Pacific region, as shown in the Pena et al. 2008 paper, and it indicates that this particular record from the southern part is not affected by the upwelling. And now, if we think about the delta 18 of the seawater record, that it shows that the northern and the southern part, as we can see in panel C, that both of them are demonstrating a similar kind of pattern. And probably they were governed by the same kind of factors related to the North Atlantic cold perturbations. And in the next part, what the authors did, they tried to draw a boundary, an hypothetical boundary between the southern part and the northern part of the Indo-Pacific Whirlpool region. And they proposed this hypothetical boundary that extends from east to west between Java, Flores Islands, and the Solomon Coral Seas. And this has been done based on the comparison of the marine and terrestrial records of from both the part of the ITCZ. And what we can see that this the gray color, the chocolate gray color the points are representing the area with lesser rain, and the blue color circles are representing the areas with higher rain. So that has been used as a criteria to distinguish between the northern and the southern part of the Indo-Pacific Whirlpool in terms of precipitation difference. And this difference between the northern and the southern part of the Indo-Pacific Whirlpool in terms of precipitation could be associated with the complex mountain island range, like the mountain range configuration and the sea level changes that the authors proposed in their paper. And the next paper or the next work was about testing the sensitivity of tropical Pacific SST to greenhouse gas induced radiative forcing. And the work has been published in 2017. And so this is the figure from that paper, but we can see that this orange color data points are representing the SST that has been reconstructed for the last 4 glacial interglacial time periods. And the orange color dotted line is the modern annual average for the region. And the panel B are actually representing the difference in the radiative forcing induced greenhouse like the greenhouse gas concentrations. Or the radiative forcing, actually greenhouse gas induced radiative forcing. So this is the difference between the average and what has been calculated for the past. So what we can see that for the SST record for the last 4 glacial interglacial time periods, it varies from around 24 degrees Celsius and it goes to around 30 degrees Celsius in some of the time periods, like marine isotope stage 5 and during the time of marine isotope stage 9. So, and the next part is in comparative comparison of the SST anomaly, that is with respect to the modern and how much we are getting for the reconstructed SST that has been plotted here as a red line, and the difference in the temperature for the or the temperature anomaly that has been reconstructed for the Antarctic region. And if we see the panel A, we will be able to understand that there is a both the pattern goes very similar with each other. And in panel B, actually, it has been shown like with both the records of temperature in terms of 2925 derived SST reconstruction and the temperature from the Antarctic region. And if we compare it with the PCO2 concentration, both are very highly correlated. So it suggests that there is an influence of high latitude climate on the Solomon Sea, and this is possibly by the oceanic tunnel connections. And so then it was like a test for the sensitivity test for the uh, temperature with respect to the greenhouse gas concentration. So the authors did a cluster analysis and segregated into two different parts or clusters. One is above to 220 ppm concentration. One cluster is the, lying above the 220 ppm CO2 concentration. That has been marked by the red color, and there is another cluster which is below the 220 ppm PCO2 concentration, and that has been marked by the blue cluster. And they had shown that there is a change in the slope which indicates a non-linear sensitivity. So what they have done further, they compared this record with the other records from the uh, eastern and the western part of the Pacific region, and the the other core locations are also shown in this particular figure. And so this is the comparative plot. What we can see that, so other cores are ODP 806 and MD 972140 and ODP 871 uh, from the western part of the Pacific. And then we have MD 2925 also from this particular region, and then ODP 1240 and TR 163 19. These are from the eastern part of the Pacific. And what we can see that all the records are showing some kind of changes in terms of the sensitivity. So the authors proposed an hypothesis or explained it, this nonlinear sensitivity uh, uh, using using some kind of hypothesis, and that is that the gradual melting of the sea ice in the sub-Antarctic zone that releases the CO2 during the initial phase of the glacial termination, and then it sets the first stage of the SST and response of SST with respect to the greenhouse gas, and then the positive latent heat and the sensible heating happens, and that triggers a sudden retreat of the Southern Ocean sea ice and a rapid increase in the PCO2, and it leads to a warming and a better ventilated uh, SAMW and AI and AIW, that is the that is the Antarctic Intermediate Water and the subantarctic mode water. So this sea ice driven mechanism they have proposed in this paper. And the next section is a very detailed study about the vertical thermal hydrological variabilities over the last 568 kilo year for the Solomon Sea region. This is a recent publication by Lilo, River, Christian Didin, and other colleagues that recently published in Quaternary Science Reviews, like in 2022. So in this in this work, first, in order to explain this work, let me explain this figure first. So the orange color box that you are seeing in this map is actually the study region, and then the vertically how the salinity and the temperatures are changing in this particular region has been shown. The annual and December, January, February, and June, July, August. The data set representing these time frames are actually depicted as shown in the legends. The red lines are actually represents the salinity variability from 0 to 250 meter depth, and then the black lines are representing the temperature variability from 0 to 250 meter depth in this region. And the authors chose two species. One is G. ruber, and another one is Pulentina obliculata, and G rover is was used to reconstruct the SST based on magnesium by calcium ratios, and then stable isotope measurement was done to get the delta 18 of carbonate information, and both these were combined together to get the delta 18 of the seawater. And then similarly, the Pulentina obliculata was used to, for the for upper thermocline temperature reconstructions, and also the stable isotope, using the stable isotope ratios, they calculated the delta 18 of the seawater, and then they tried to see the differences that is depicted by the delta T and delta 18, and of the like the difference in terms of temperature and the delta 18 of the seawater for this particular region over the 568 kilo year time frame. So this is their result. So here you can see that there are as the legend has been marked here. So the red points are representing the data set from the uh, Globigerina ruber, and the blue data points are representing the Pulentina obliculata species, and you can see from panel A and B is the delta 18 of the carbonate of the shell, and panel C is the SST determined from the magnesium by calcium ratios from the ruber, and panel D is the UTT from the Pulentina obliculata, determined again from the magnesium by calcium ratios, and the then panel E and F are the seawater calculated from the ruber and Pulentina species respectively, and the bottommost panel are actually the is the LR04 stack, that is the panel G. So what we can see that if we focus on panel C, or then we will be able to understand that SST variability during this entire time period ranged from 24 to 30 degrees Celsius, and this long record are showing that MIS 7, 13, and 15 are relatively cooler interglacial than the Holocene MIS 5E, 9E, and 11C. Those are the warmer interglacials. And the glacial maxima actually, in terms of SST, they registered the similar temperature throughout. It is around 24 degrees Celsius. And if we think about or look at the UTT, that so we will be able to understand the variability is from 20 to 26 degree Celsius here, and it shows that the subsurface temperature showed the similar peak around 24 degrees Celsius, and the glacial maxima temperature is around 21 degrees Celsius. That is also similar throughout the record. Now we are seeing the differences between the ruber and the Pulentina record. So panel A represents the differences in the delta 18 of the carbonate compositions, that is difference between Pulentina and ruber, and panel B actually represents the differences in the temperature reconstruction, SST minus UTT. Panel C is differences in the reconstructed seawater composition. In this case, it is ruber versus Pulentina. And panel D is the LR04 LR04 record. So what we can see that there are sudden time intervals when there is a rapid shift or in terms of delta T, and they are as shown by the red color arrows, And then there are certain time intervals. There was a rapid drawdown in terms of the temperature. So, actually, and throughout, if we see the overall record, the temperature difference actually it is relatively stable as like from 3 to 5 degrees Celsius as compared to the present day. And so, as I was mentioning, like during the termination 3 and during the termination 2 and 5, that there is a relative increasing trend, and then there is a sudden drop that we can see, or the decreasing trend in termination 3, termination 4, and termination 6. And also what we can see that the highest and the lowest thermal gradient occurred right after the glacial termination period 120 kilo year, and then around 240 kilo year. That is, those are the time intervals marked by this dashed line. And then if we see the delta 18 of the seawater record, it shows a clear salinity contrast during the which ranges from around 0.25 to around 5 per mil throughout the past 6 termination. And the very important take-home message or interesting thing to note that if we try to understand the role of temperature in controlling the stratification, then we'll be able to see that during the MIS 5, 9, and 11, these are the warm interglacials when the delta T is very large, but the changes or the difference in the delta 18 of the seawater is rather small. That is those. So these are the time periods when the thermal contrast is more important in driving the stratification. However, if we look at the MIS 7 or MIS 13 time periods, those are the cold interglacial, then their temperature contrast is rather small, but the salinity contrast is relatively large. That means the temperature is not the critical parameter driving the stratification during these time intervals. Also, in this study, they had carried out a detailed spectral analysis that showed that both the surface and the subsurface delta 18 of the carbonate and the temperature that showed the persistence pattern of or the dominance of 100 kilo year, 41 kilo year, and 23 kilo year cycle. And in this particular paper, authors also discussed about the role of this orbital forcing controlling the Solomon Sea thermocline, the structure, and in controlling the regional ocean circulation, and also exclusivity of the each and individual termination period. So this particular paper is a very detailed study on this, covering these aspects, and for this particular study, I will leave it there, and I hope that in future, some of my senior colleagues who are working on this particular core and the associated core from this particular region will be able to give more valuable information and more holistic picture in terms of SST and UTT variability in this particular region, like in the Solomon Sea region, in any of the future talks. So with this, then I will move towards the next section, which is tracking the precipitation using the Globigerina ruber rare earth element by calcium ratios. So the initial paper, or the first paper that came out in 2015 was led by Liu et al. And so in that particular paper, they proposed or they had shown that the relationship or based on the neodymium by calcium ratios from the Ruber, they reconstructed the precipitation history. So what is happening here? Like for I will try to give you the concept about using the rare earth element ratios or the neodymium by calcium ratios as an indicator of the precipitation proxy. So these rare earth elements are the they are they are the inputs from the terrestrial realms that is driven by the monsoonal precipitation, and that is through river discharge it is coming in between and getting trapped in the lattice of the carbonate lattice of the forum. So Ruber is like the rare earth element proxy from rare earth elements from the Ruber are actually is a proxy for the weathering, and weathering in this particular region is controlled by the monsoonal precipitation. So what we are seeing here is a proxy of a proxy. So in that way we are connecting the neodymium by calcium record of the Ruber with the local precipitation with the precipitation pattern of the region. So what we can see in this figure is very interesting. So panel D is actually not panel D, sorry. So panel C is actually the Globigerina Ruber neodymium by calcium variability for last 282 kilo year that they had retrieved. And now, if we see the other parameters, so first let us focus on the southern hemisphere. Like as we know that the precision is one of the controlling parameter of the precipitation. So first let us have a focus on this southern hemisphere solar insolation at the 15 degrees south location, and what we can see that the green bars are representing the time periods when the southern hemisphere solar insolation is high, and that is leading the higher precipitation. So if the neodymium by calcium ratios in the Ruber goes high, that means the precipitation is higher. So during all these green marked by the green color bars, these time intervals, the southern hemisphere solar insolation is higher, and the neodymium by calcium ratios in the foraminifera or the Ruber shells are higher, indicating a higher monsoonal precipitation. However, this is not the case throughout. So the gray color, if we focus on the gray color bars, these gray color vertical bars, these are also the time periods when the southern hemisphere solar insolation is high. But if we look at the Ruber record, then it is lower. That means the precipitation was lower. So these are the time periods, even though we have higher southern hemisphere solar insolation, but the precipitation was lower. So the question is that what is that unknown beast that is coming into the picture periodically, and that is diminishing the absolute dominance of precision controlling the precipitation pattern over the Papua New Guinea region. So the author proposed an unique mechanism operating through driven by the obliquity, and it is a pressure push mechanism. So if we see, it is being the mechanism I am describing it here in this right hand panel. So actually, the movement of ITCZ is driven by the interplay of South Siberian high and the Austral low, two different pressure zones. So what happens that during the high obliquity time period, there is a pressure push from the Siberian high, and then what happens that the ITCZ moves towards the more southern part, and as a result of that, the Australian sector receives more rainfall, and the sector that is near the Papua New Guinea region receives lesser rainfall. And during the time of low obliquity, what happens that this ITCZ moves towards north, and as a result of that, the Papua New Guinea region receives higher rainfall. So now with this background, if we now reinterpret this data, so these green color vertical bars are representing high southern hemisphere solar insolation that is driving the higher precipitation. But the gray color bars, although the although we have high southern hemisphere solar insolation, the precipitation is low because there is a high obliquity sitting over here. So during these time periods, the ITCZ was pushed farther towards the southern part. As a result of that, the Papua New Guinea region was receiving lesser rainfall. So what we did now, that we tried to extend this record for the last 600 kilo year. So this is the methodology part of the work that we are doing. I am not getting into the greater details, but what is very important that in case of rare earth element analysis of the forums, it is recommended, or it is very crucial that we should get rid of all the iron manganese coating sitting out at the top of the forum test. So a detailed protocol was followed in this during the course in order to get rid of all these coatings, and before putting the solution in the mass spectrometer, before like diluting the test and putting it into the mass spectrometer. And details of this method are available in a paper by Shen et al. 2010. It was in analytical chemistry, and there was another paper, Lee et al. 2014. It is there in Journal of Asian Earth Science. So we followed the protocol that has been described in those two papers. And this is the results in terms of past normalized values. So I will go from the bottom towards the top. At the bottommost panel, you can see that the rare earth element pattern for the Papua New Guinea coastal seawater, that is in panel G. In panel F, the green color points are representing the rare earth element pattern for the Papua New Guinea river, and then it is followed by panel E, which shows the rare earth element pattern at the Papua New Guinea corals, and then it is followed by the coral of Great Barrier Reef and the East Pacific Sacculifer in panel C and D. Panel B are actually the results from 0 to 282 kilo year that was investigated by Liu et al. 2015. And panel A are from the present study, where we extended this record further till 600 kilo year. And so that is represented by the orange color dot. So both these orange color data points and the blue color data points, they are similar. That means and so it indicates the source were constant throughout this throughout this last 600 kilo year. And this is the result of the present of the study. And this is the entire 600 kilo year record that I have shown in this figure 1. So in the x-axis we have the time, and then it has been, and the y-axis we have this neodymium by calcium ratios in micromole per mole. And what we can see that if we look carefully, the time period during the around 400 to 600 kilo year and 400 kilo year to the present day, there is a shift in the baseline, and also there is a change in the amplitude in the cluster of data. And then we carried out the wavelet spectral analysis of this entire record, and our record shows a very interesting pattern. Like throughout, we have the precision cycle, and also it is very interesting to note that, and also till 82 kilo year we have this obliquity cycle also. But it is very interesting to note that there is a dominance of 100 kilo year cycle in the record from around uh, after 300 kilo year, and it persists till 550 kilo year. So in the next stage, we carried out a model simulation uh, and tried to reconstruct uh, the precipitation history at different condition using an HCM3 model. And so there are four outputs or four group of results. One is A orbit or orb, that means the orbital forcing, and then orb CO2, that is orbital forcing with CO2 forcing. Then orb ice, that is the orbital and ice sheet forcing. And then we have orb CO2 ice, that is the orbital forcing CO2 along with the ice sheet forcing. So the output is about on these four different condition that we set for reconstructing the precipitation pattern. And few the initial condition uh, is mentioned here in the bottom panel. So this is the result for the model precipitation of the Papua New Guinea region, and this we have focused for the 5 degree to 12 degrees south actually. So what we can see here that for the orbital condition in the Papua New Guinea region, the simulated result shows that for almost all the conditions like orb CO2, orb ice, and orb ice CO2, we have the precision present here. Uh, However, when the orb CO2 and orb ice CO2 conditions, these two conditions, um, they this in these two CO2, these particular groups, we have a dominance of 100 kilo year cycle. And then we compared our result. So we further simulated it for the Northern Australian part. And in the upper panel, you can see the December to April precipitation for all the four condition: orb CO2, orb ice, and orb CO2 ice. And the bottommost panel are the wavelet spectra for all these four conditions, and during for both these regions. And what we can see from the upper panel also, like the reconstructed patterns are quite different from each other, like for the Papua New Guinea and the Northern Australian part of the this Western Pacific Wampool region. And if we see the wavelet spectra also, I have already described the results for the Papua New Guinea region. But now if we see the Northern Australian part, precision is dominating throughout, like for all four conditions, like orb CO2, orb ice, and orb CO2 ice. And with so what we thought like this modeled simulation actually provides us two inputs. One is for the Papua New Guinea region. Um, there is an indication of the presence of CO2 and ice sheet forcing probably. And then there is a regional heterogeneity that we are seeing in terms of reconstructed precipitation pattern for this part of the Western Pacific Wampool. And now this is a composite result where I have put all the parameters, like we have the Southern Hemisphere solar insolation, neodymium by calcium ratios, we have precision, obliquity, we have the eccentricity also, and I have put the sea level changes and the CO2. So what we can see here that throughout our record, So initially, I showed that the pressure push mechanism was active till 82 kiloyear. That has been shown in Liu et al.'s paper. Now, in this extended record, also we saw the persistence of this particular mechanism where precision in tandem with obliquity is controlling the precipitation pattern over this Papua New Guinea region for the last 600 kilo years. So the pressure push mechanism is working throughout this time period as demarcated by this green color and the gray color vertical lines. So green color vertical. So as I explained before, green color vertical lines are representing those time periods when the southern hemisphere solar insolation was higher, driving the high amount of precipitation, and the gray bars are representing those time periods when the southern hemisphere solar insolation was higher, but the precipitation was lower because of the high obliquity that was forcing the ITCZ towards the more southern part. However, close to 370 kilo here, there is a unique configuration of the precision parameter. The precision was very low, and there are two small fluctuation comes under one obliquity maxima, and during that particular time we have a higher precipitation also. So and so this is one of the time interval when this pressure push mechanism, like we can't the pressure push mechanism is not working, or something else is happening in this particular uh, uh, time period. And in this particular figure, the yellow shaded region are representing the time period when in the wavelet spectra we got the dominance of 100 kilo year cycle. So, and this is around 350 to around 550 kilo year. So we have reconstructed around 600 kilo year monsoonal precipitation history using Globigerina record, Ruber neodymium by calcium record from the ND 0529254. And throughout our record, our record shows a persistence of obliquity and precisional forcing, and the pressure push mechanism that is controlling the precipitation over this region. And there was an appearance of the dominance of eccentricity cycle that can be documented around like it starts around 350 to 400 kilo year, and during that time period, and it was there from 350 to 550 kilo year. And probably the low precision during that point of time, along with the lower amplitude for the of the obliquity might be responsible for the appearance of the 100 kilo year cycle, because maybe because as those parameters like the precision was lower and the amplitude of obliquity was relatively lower, so maybe during that point of time the high latitude forcing was kicking in into the into our record. That's uh, we are thinking as of now. So before finishing this talk, uh, I would like to uh, express my heartfelt gratitude, firstly to Professor River, because when I joined here, it was a peak COVID time in uh, the end of 2020, and during that crucial time period, not only he offered me this postdoctoral fellowship, also he and Dr. Lolig, they offered me, or they in, included me in this very exciting and interesting and a new project for me it was. And so I'm very much thankful to them for their support. I am very much thankful to the high spec and the paleoceanography lab members for teaching me many things, starting from the picking the forams, cleaning and running the machines independently. I would like to thank the History of like Science of Technology, now the NSTC Taiwan for funding, and our collaborators for cooperation. And in NTU Geoscience, we have a PP group meeting, Paleo group meeting that used to happen. So I am thankful to the members who had given me valuable suggestion during this course of journey for the betterment of this project. And I would like to finish this with a quote by Sir J.C. Bose that the past shall be reborn in a yet nobler future. So as natural scientists, especially, it is very relevant for the kind of research that we as a community are doing, and hopefully all of our results will yield valuable information to predict the future in a much better way, and so that as a community we will be much more prepared to deal with the scenario, like to deal with the issues of the climate change in the future in a much more better way. So to make the the future better. So with this, I would conclude. Thank you for your attention, and I will
Excellent.
be I
Thank you
will
so
be
much.
happy to take any questions and your suggestions.
So we'll let everybody have a moment or two to put any burning questions that they have into the chat, so you can type those up. Or if you're here attending live, you're more than welcome to raise your digital hand, and I can call on you for your question. So while everyone is coming up with their questions, I just have a quick question, and this could be related to my ignorance as mostly a terrestrial researcher. So when you were talking in a prior study about the salinity stratification and its relation between kind of both temperature control as well as other types of control, and then now with your work, you're kind of highlighting similar types of control on the temperature and the salinity in terms of how it controls stratification. Do you have any, I guess, insight you can lend to that with your own work?
Regarding the salinity stratification work, actually, that was the 2022 paper that I mentioned, where they have compared the Ruber record and the Pulentina obliculata, two different species actually, and then their SST and reconstructed delta 18 of water with that information, with that differences, they tried to infer about the stratification and other scenario. For my particular record here, I have focused mostly on the Ruber, like the single species. However, I know that some of my colleagues that I have not done that work, but I briefly remember seeing a glimpse of a plot where they did it for the multiple species, and there it was interesting. I can't recall exactly the time frames. In some of the time frames, the records shows distinct pattern for different species, the neodymium by calcium ratios, but in some of the intervals they are clustering together. So there is another pattern. So probably from like someone else who is working in that aspect will be able to share a more interesting story in that aspect. But that's a very interesting question, like to compare the story built from magnesium by calcium ratios and the stable isotope ratios and the scenario that we will be getting using the rare earth element. Yeah.
Yes.
Yeah. I could able to answer you clearly, or anything else you need?
No. I think highlighted maybe some of the differences between your study and what I had been thinking. Yes. I do have another question, which is somewhat related to this. So This is always a problem in the community, right? Is when we're looking at precipitation, we often look at total precipitation, but we're also interested about the seasonality of the precipitation and how that might change, especially with shifting essentially ITCZ, for example. So can you also provide any insight as to how might the seasonality of rainfall might have shifted or not over essentially the record in which you have been looking at?
With the present, so this is also another interesting question. I also had a thought about this seasonality perspective, because my previous work, actually during my PhD time, I worked on the seasonality was on the mollusk shells. So as using the isotopes chronology, you will be able to infer you can go to that resolution. But with my limited knowledge working on the forums, I don't know if we can go up to that scale. We can resolve it to the seasonal resolution or not. And also, there is the proxy that we are using is neodymium by calcium, as I presented during my talk. We also don't know, at least at the moment, that how much precipitation change will result the change in the amplitude in the neodymium by calcium, actually. So I thought in that line, I didn't, so probably I don't know, like not even the ratio, like if some of the clues, because in that particular region, a lot of geotracers cruises that happened, and they did a lot of water sampling at different time periods. Probably if I have not done that exercise yet, but if we have some control about the month, like and if we compare the data, maybe we have some idea to start with, that this much of changes leading to this change, like this much of salinity change or precipitation change leading to this much of change in the isotopic composition in the coastal seawater. Also, in these regions, because these regions are actually tectonically active also.
Yeah.
So another aspect I was also thinking about, although these are not beyond the scope of the present study, about the role of the groundwater discharge or sudden freshwater plume that will come and in the surface water, that will also affect the surface chemistry. So these are the some critical avenues which needs to be addressed and probably will be addressed in the future.
Yeah, it's as you said, a really exciting region, and there's so many things that we still need to figure out.
Yes,
I'm glad that you mentioned the part about the sensitivity of the proxy itself, because I always did kind of wonder. I mean, that's something I also like to think about, is, how well do we know what we think we know? Which
definitely.
is of course a key question for any scientist. And I don't see any other questions. So I have one very silly question. Again, probably an ignorance thing as a terrestrial person, is what is an oceanic tunnel? You mentioned that in one of your studies.
This is, I think this is kind of a teleconnection between the I think
Oh wait, I think I see. I
can ask.
Jerome Grunfeld. I think I saw a message from him pop up.
Yes.
Yeah.
Hello.
Can you? Hey. Can you hear me?
Yes.
Yes.
Okay. Very good. I would maybe the question. Maybe I can. I've asked this before in the seminar here. So in that case, my apologies for it. But I probably don't remember it then. Before that, I wanted to point out that maybe an idea on this seasonality is actually one way is to look at a proxy for dust, because we have done this in Northern Australia, where you have on one hand, yes, you have the monsoon, the rain proxies in the Delta 18 with the seawater in there, but you also have, if you look at different elements coming from different minerals, then some of those are being provided by the rivers, and some of those are only provided by dust. Meaning, if you find both of these elements in your records, then you have a very strong indication that you had both a dry and a wet season in there. And I think a lot of these records probably already exist for your site, because based on XRF measurements and things in there, I mean, they usually put the whole package of different elements in there. So that may be interesting. And say like the river ones are typically like potassium or titanium. But if you look at heavy elements like thorium or uranium, those are more coming by dust. So that may be an interesting one. I'm not sure if you get a lot of dust directly from Australia, but maybe the highlands in Papua, they may be providing dust sources in there, but it may be interesting to look for. Yeah. But what I wanted to ask was, I said maybe I asked it previously already, with the neodymium, how do you know it's really the surface signal in there in that? And it's a bit follow up from what Tara also asked in there. Because normally with neodymium and the neodymium isotopes, this is basically always a signal, a benthic signal, because it's measured in coatings. And so basically, even if you take surface forearms, it will be a bottom water signal. And with the cleaning, you can remove those coatings, but it's only the oxide coatings and the hydroxide coatings. So any of those inorganic carbonate coatings, which are being formed in the sediment, they will still be around. And they would give you a benthic signal in there. So maybe you have looked at the solutions after your cleaning, so basically your waste products, to see if what the neodymium was in there, like if you're actually really removing neodymium from coatings in there.
So we did that exercise on the like we measured neodymium isotopes based on the cleaned forum and also the unclean, like the residual part, and like whatever is getting leached out, that fraction. So and both are distinctly different from each other actually.
Okay.
So that gives us some confidence about okay, the signal that we are getting is actually coming from the test.
Yeah, but do you know in that sense then if this is really surface? I mean, so if it's coming, so no, I guess your distinction would be it's if it's in the residual, so then that the signal from the coatings, so from the oxide coatings, that is what you're removing, but you still don't know what is in the carbonate coatings, right? So maybe it's an idea to do some measurements on benthic forums and see what comes out of that.
Okay, I see. Thanks for your input. Okay,
just as an idea. Okay.
Okay, thank you.
Thank you. And then maybe if I may, one more then.
Yeah.
Okay, well, I think we've reached, oh, sorry, I had a little bit of a lagging issue there. Sorry, I didn't mean to cut anybody off.
Shall I go back a little bit?
Yeah, please go on.
Yeah.
If time is there.
No, so I'm just wondering, like you see it more and more that these days, if you have high resolution or those records from Lilo, and also the terminations are quite high resolution, and you see the nice distinction between either northern or southern hemisphere signal in there. What have you done, or has Lilo done any breakpoint analysis on there? Because then I mean, you had it in some of the plots also that you put arrows in there, like here's a big change and here's a big change. But I think these days, this is breakpoint analysis and high resolution records, we can actually pinpoint it quite nicely down. And then probably the result is the same, but at least, yeah, you have it. It's maybe a little bit more exact than simply saying like, well, it looks like the arrow is going to be here with the thing in there.
No, breakpoint analysis we have not done yet, but thank you. I will keep it. I have noted it down. Thank you. Thanks for your input. We have not.
Okay. Thank you.
Come.
Okay, well, I think that brings us up to the end of the talk today. Not just because I do have to run away for another meeting here at 1:30, but let's please put our hands together for our wonderful speaker for today and his excellent summary of all the work that has been done, as well as introducing some of the really exciting results from his postdoctoral research at NTU. So let's put our hands together
And
for
thanks,
this week's talk.
thanks to you, Peter, and other organizers of the Monsoon Seminar Series for giving me the opportunity to present my results. So my heartfelt gratitude. Thank you.
Thank you. And so thank you for all for attending today. And so before you all run away to complete the rest of your days, next week we do have another talk on Schedule A, and we will be joined by Ray Zammit, who will actually tell us a little bit about the North African monsoon in Malta. So please tune in next week if you have the time, or catch us here again at YouTube or the Zoom recording. And so with that, I hope I see you all again next week, and have a nice rest of your day.